All right. So we're just going to work on two problems here. We're going to do precipitation problems. We're going to identify how much precipitate we have in a certain situation. Let me plug this in here first. And again, I've been hearing rumblings about how I don't prepare you for every homework problem in the back of the book. That is true. I don't have time to go through every homework problem that you will ever see. I hit the big concept, and you got to be able to go in the front door, the back door, the side door, through the window, through the chimney, all different directions. Okay? That's what they're going to do in college. They don't have time to show you every possible alternative way of doing a problem. Does that make sense? Okay? Now, I do my best to try to get you prepared, but there's a point where you got to go beyond and do some thinking yourself. Cool?
Yeah.
All right. So, first problem. All right, it says calculate the mass of solid. Ooh. Not good. Of solid NaCl that must be added. So what we have is a solution. That is the stuff about our solution. We know the volume of our solution. We know the molarity of the solution. And it wants to know how much solid of this would I have to add to the solution so that I get all of the silver ions to precipitate out. Okay? Now, remember when we talked about dumping things together, it's possible that ions from one will react with ions from the other. Right? You remember that? And if you look at your rules, which you don't probably have in front of you, chlorine usually stays in solution unless it's with what? And it should say in the exceptions, I think it's 2 or 3. Unless it's with silver. So what's happening is it wants to know how much of this would I have to add to this so that the chlorine will completely react with all of the silver ions and precipitate out completely. Does that make sense? Okay? So in order to do this, we got to figure out how many moles of silver I have in here. Because I got to know how many particles I got to precipitate out, correct? All right, let's do it. How would I get moles of silver from this information? Okay, I'm probably going to start with the liter just because I'm going to use this as a conversion factor. But you're on the right track. Okay, so I know the volume. I know how much moles I have per 1 liter, but I don't have 1 liter. So, make sense so far? Nothing crazy. Technically, this is the moles of AgNO3. Following so far? Okay, but let's make, this is where you have to think kind of outside the box, where I was talking about parts versus whole. Okay? When I take this times this, I will get moles of the whole thing. But we want moles of what? Ag. But what's the relationship for the whole thing to the individual particle?
1:1.
It's a 1-to-1 ratio. So if I get the moles of the whole thing, do I also have moles of the silver ions?
Yeah.
Okay. That's important to be able to make that connection. Anybody struggling with that?
So how do you know it's a 1? Because there's no coefficient.
Yeah, it's a 1.
Okay.
Okay? And then if this were like 2, Ag2, I would have to take this number and multiply it by 2. The answer of that. That makes sense? Or if this was 3, it just means for every 1 of this, I have 1 of this. Every 1 of the whole thing, I have 1 silver. That makes sense? If it were 2 silvers, for every 1 of the whole thing, I would have 2 silvers, and you'd have to multiply that number by 2.
So would you multiply or divide by that?
You would multiply it because you have twice as many silvers as you would have. And remember, twice as many. Moles is an amount number,
Yeah.
right? It's not something else. So if I know that I have this many moles of the whole thing, I have twice the moles of silver when it breaks up.
Okay.
Okay? So then we want to know, now that we got, so essentially we have moles of Ag here. Okay, because I'm assuming that the answer here is just going to be moles of Ag because that's what I want. Okay, now, if we look at this is what we are adding, correct? Okay. What is, if I were to take this and write it out, this is technically my precipitate reaction, correct? That's what's happening. We've got silver reacting with the chlorine, okay? Well, adding this is going to introduce the chlorine. Here's another ratio we have to identify. What is the ratio of sodium chloride to chlorine ions? It's also 1-to-1. So if I treat it as the whole, do I really have silver or chlorine ions? Okay? And I know that your ratio here is a 1-to-1 ratio. We've identified that. For every 1 silver, for every 1 sodium chloride, I get 1 chlorine ion of it. And lastly, what did it say we were solving for? Mass. Well, let's find the molar mass of sodium chloride. We're done. What is it? 58.44. It's a little bit of a thinker, because you got to look at the relationships between. Now, most of the time, I'm probably going to give you 1-to-1 ratios for everything, because it's a little bit more advanced to add different ratios, but it's possible.
Is that the mass of silver chloride or sodium chloride?
Sorry, sodium. I kept saying silver, I know. So what it wants, if you look at this, it wants to know how much sodium chloride would I need to add to it to get all of it to react. So we're trying to figure out, well, I have so many moles of silver, therefore I need the same amount of moles of my sodium chloride so that it will completely react. That makes sense? And since sodium chloride is a 1-to-1 ratio with the chlorine, I can just find, I don't have to do another step. Okay? So I'm going to save you time so we can go on to the next problem and just do all this math for you, because I know you know how to do it, right? 8.77 grams of sodium chloride. Now I want to show you something just so you can understand. I'm going to see, I've never done this, I want to see if this works. Okay, I want someone to take, well, what is 1.5 times 0.1? What is it?
1.15.
And we said that was the moles of the whole thing, but was the same as the moles of the sodium, right?
Yeah.
Would you agree with that? Now let's take this and multiply it. So this is the mass, right? Multiplied by the molar mass, or divided by the molar mass. And that will give me moles of the sodium chloride, correct? Someone do that. .15.
Yeah.
So that is moles of NaCl, but remember we said it's a 1-to-1 ratio of. So do you see how I have the correct ratio needed? Because it's a 1-to-1 ratio for this guy to precipitate, correct? So I better have enough chlorine to match the sodium so it will all precipitate out. Does everybody see how that works? Never done that before. That's pretty cool that you do that. Yeah, you'd have to double it somewhere or triple it somewhere, but yeah.
Is all you have to do is change the middle step, like 2 to 1, 2 to 1, 0.
Or 1 to 2.
Yeah, essentially.
Or a 1 to 2. 1/2.
Yeah. This helps seeing that you can visually see how all this stuff makes it so they're equal so that they precipitate out. Because if I only have 0.13 of this, will it completely react with all this? No, you'd be left with some silver ions in solution, and therefore you wouldn't have done the problem correctly. Cool? All right, do another one.
Does that carry over to real life as well?
What do you mean?
Is that just theoretical? Or if you put
Yeah, well,
0.15, I mean, it
everything in real life is not going to work
I mean,
perfectly.
it may take a while.
But in theory, yes.
Okay.
You know, is it possible that a bunch of water molecules shield like one small little particle from completely breaking out a solution? Like, could there be, you know, a sodium or a chlorine way over here and a silver way over here, and they never ever get to contact with each other? Is that possible? Yes, but the majority of it, we're assuming all of it comes out, which in chemistry it never works that way. But yeah, how do we know how much we know perfectly? Okay? Alright, this one, a little bit more difficult. That'll make more sense. Whoops, wrong one. So hopefully I can give you some time in class, unless this takes 16 minutes. I hope not. Alright, so it says, now we got two solutions. That and that, and they are mixed. Okay, remember what we did the other day, and we showed how cation from one can react with anion from the other, and anion from one can react with cation of the other. Okay, first and foremost, will sodium form a precipitate with nitrate? No, it's group 1, and nitrate's always very soluble, right? So that won't happen. But we know that sulfate normally is soluble, but not when it's with lead. So that's going to precipitate out. Okay? It wants to know how much of it will we have when it precipitates out. Now we're assuming it will all precipitate out. Okay? But we want to know how much there's going to be there. So what I would do with this, just to kind of see big picture here, would be to write like the whole equation. So we know that we have this. Oof, lovely. And this are added together. We know that a precipitate will form. There's your solid, right? And now the other would be what? Your sodium and your nitrate. And sodium is a 1+, nitrate is a 1-. Now remember, aqueous represents that they're actually in ion form, right? So if they're not actually combining, does that make sense?
Yeah.
This is not actually combining. It's just saying they're still in ion form.
What if you like boil it down, it would combine?
Yeah. Okay? So there's our big picture here. However, I probably also should break up this into its net so I can see the relationship between the ions. And thankfully, it's a what to what ratio? What? 1 to 1. Okay? I'm going to go too fast here, we'll take our time. Following so far, any questions? I know I haven't really done a whole lot, but give us what? I mean, they gave us all the information. I'm just showing it all in an equation. I just like to do that. You don't have to if you don't want to. Okay, it allows me to see relationships, ratio relationships a little bit better. I'm very visual, so if you're good just looking at it the way it is, you're fine. Okay, now I want to make something very, very clear. Where does the lead come from?
The lead nitrate.
Yes. Where does the sulfate come from?
The sodium sulfate.
So what I have to do is I have to look, and based on the information they gave me, I got to figure out how much moles of sodium sulfate or sulfate I have, and how many moles of lead I have. Okay, so we're going to do that. Starting with, what's the first one that comes up here? Lead nitrate. Okay, so I have 1.25, not moles, that's wrong, liters, and 0.05 moles per 1 liter. My PbNO3 2. Okay, here's the ratio thing again. I want to know, I want lead, no, yeah, I want lead, right? Do I care what the nitrate is? No, it's not going to precipitate, so I don't need to know the number of moles of nitrate. I want to know the moles of lead. So what is the ratio? 1 to 1. So I know that when you get this number, which is 0.0625, yes, that's the mole of the whole thing, but it's also the mole of lead ions because of the 1 to 1 ratio. I should put moles in there. So I could write because 1 to 1 ratio of PbNO3 to Pb2 plus. Okay, as long as you guys remember that I can assume that this is the same as the moles of the whole thing because of the ratio. That is very important. Okay, what if I wanted nitrate ions? What would I have to do with that number? Multiplied by 2. Okay? Second one. What do we got? 2 liters? And 0.025 moles. Is that right?
Yeah. 0.05.
Again, this is Na2SO4. Let's check the ratio here. What is it?
1 to 1.
1 to 1 because it's sulfate I want, correct? Everyone following? All right. Now, the question is this a limiting reactant problem? It is.
It is, yes.
Now, let me explain why. This is my precipitation reaction, right? What is the ratio of lead to sulfate needed to produce that? 1 to 1. So I better have the same amount of lead as I have sulfate for them to react both to completion, right? But do I? That is your what? Which means all of this will get reacted, but there'll be some lead ions left in solution, won't there? Okay? Now that's not technically what they asked for. They didn't ask for excess. They wanted to know how much mass of this I would have. Well, I know that 0.05 moles of lead is going to be what limits the reaction, but isn't that going to also be a 1 to 1 ratio to this? So can I do this? Everybody see it? You ever see what I just did? Do you see how many times I had you connect ratios here and finding what the ratio was? I could have taken, guys, 0.05 moles of PB. I could have set up a conversion factor and said, oh, for every 1 mole of PB, I have 1 mole. Well, I've just been multiplying that by 1, wouldn't it have? Does that make sense? Okay, so I'm trying to save you the step of putting a conversion factor where you're going across the bridge and just putting 1 divided by 1.
So if they're not 1 to 1, you just do
You either would take care of it when you would do it. Well, you probably take care of it in the.
take the limiting reaction.
Yep. Like if this were a 2 here, I would take my limiting, I I would set up a conversion factor, and for every one lead, I would have 2 of the whole thing. Now that's not even possible, but you get the idea. Right? It would probably be 2 of this would give you 1 of the other. Okay?
It'd be 3 negatives.
Wait, no, that's just.
So now just to finish,
That's one.
what do we do?
That's one.
Only
plus.
Pull a mass and you're done.
Times.
303.3.
3
Yeah. 303.3. I broke my rule of going to
303.27.
fuck. Broke my rule. You can fix it. I don't care.
What?
Of 2 decimal places.
Oh.
And you should get approximately what, 15.2 ish.
Yeah.
Now I could go back and I could subtract 0.05 from this number to figure out how many moles of excess I had. I could then take that and use molar mass to figure out how many grams of ions are still in solution, correct?
Yeah.
Okay. Do we see how this works?
Yeah.
2 things mixed together to form a precipitate. I would write out what the precipitate is so that you can match that the sulfate that precipitates out comes from one, the lead comes from the other. It's always going to be that way. One will come from the one guy, the other will come from the other guy. You'll have to figure out how many moles of each. Okay? You have a question?
So would that be the net instead of the net?
Yeah, this would be the net matter. Yep. That's why we did that yesterday. Yeah, I could have written all of these out in ion form and then. Questions? Now, is it possible that it might look just slightly different in your homework? Possible. Okay, so why don't you open your books? You got 5 minutes, so let's take a look at these problems, maybe give you a little direction, maybe I can kind of ease the pain of some of this. What's the first one? Derived. Okay, looks like 55 is just like the first one I did today. You see it? How you're trying to figure out how much salt you need to add to precipitate all of it out. That looks like the very first problem I did today. Make sense? What's the next problem? 56. Same thing, just like the first problem looks like. And be careful, they gave you milliliters. What's the next one? 57. Alright, that looks like the problem I just did. 2 solutions. Okay, aluminum hydroxide is going to precipitate out. How much of it? Make sense? What's next? 61. Yeah, same thing. Oh, they do say calculate the concentration of the remaining ions in solution. So that would be doing what I said here, taking this minus that to figure out how many moles of excess you have. Does that make sense, right? Because it's a 1-to-1 ratio, only 0.05 of this will get reacted. The rest is excess.
But it says in solution divided by what?
Total volume.
So
Yeah, it'd be
3.25.
0.05 divided by 3.25.
Okay.
Would give you the concentration of, right? Because remember, we're taking 2 volumes and mixing them.
Yeah.
Got it? Does that kind of give you a big picture? Is that the last one? Or is there one more? Is there 2 more? Just one more? 63? I always throw one goofy one in there. I give you about 4 easy problems and then throw in a moderate problem. That's what your test booklet says. It tells me which one's the easy problems, which ones are the moderate problems, which ones are the hard problems. I never put a hard problem on your test. And I only put about 4 or 5 moderate problems, and the rest are considered easy problems. I struggle with the hard ones. That's kind of subjective. 63 you said, right? Oh boy, I'll let you struggle with that one a little bit. That was a good one. You kind of have to work backwards, if that makes sense.
How did you say you would find out how much is left over? You select for this one, or you do?
It's possible that these would be like the same, but I'm guessing one will be limiting, one won't be. So, right, if this is a 1-to-1 ratio, and I know if this is going to run out, then I can only react that many moles of the other guy, so you can subtract that from that. And then, if it wants mass, just do molar mass. Okay. I'll let you struggle with 63. If you can't get it, we'll go over it tomorrow. Because review tomorrow. Review day tomorrow. We'll review in class. What we don't finish, we'll review at night. Okay? See you guys. Again, you can come in anytime and check my key if you want. Do you remember any of that vaguely from last year at all? It had to do with solubilities. Do you remember like putting S at 2S, 3S?
Yeah.
It's essentially that type of stuff.
But very different.
Wow.
And so, we have to actually find
For food.
Yeah, we're not actually defining solubility, we're doing the stoichiometry.
Yeah,
and
yeah.
essentially what we're doing. Marte's ready.
Four. Oh, my soul.
What?
I totally forgot.
Chemistry test? This is awkward.
All right, Steve. My grade. Woo.
Mason Cole.
Are you ready for one?
I'm not so busy. Guess what? It's confirmed that we will be in touch.
Oh, wait. Kramer.
When?
And this year, when I lived with my grandparents, I did a
I
college.
forgot there was a test today.
A long time for my grandparents left, so they pulled me down.
What college?
I'm gonna go to a
So, when was it?
Ah.
sometime this summer.
Early June, me down there? All right, it's gonna happen.
I'm gonna bring all my stuff down.
All right. I'm down. But the question is, do you want to go down there?
Wait,
Stay the whole summer? Because you probably
Yeah,
early summer. Yeah.
It's the 6th.
I'd rather.
I'm gonna.
Well, I want to work for 6 months before because then the tuition is cheaper.
Oh, Mr.
That's
Right
it.
Nano.
And so actually, I'm
Today's
gonna meet
night.
my uncle. You're gonna be jealous.
That's it.
You know, my uncle's the head
It's
coach at
negative
Brentwood
first.
W, one of the largest
Oh, that's
basketball
disgusting.
schools.
There's a dead
Well, he's
prison.
assistant, so I get to ride with him every tournament and get on boats and stuff.
Good
job. Dude, it's gonna be awesome because I get to ride with him and go on the boat and stuff and help weigh in, fish and everything.
barely.
Oh,
with all the professionals.
So jealous, man. Oh my goodness.
Don't feel
Alright,
bad.
what were you saying, Gage?
I'm gonna show you this video. Video, I don't remember what
that'd be negative 6.
I was gonna show you a video about Penn State. There's this tackle.
Mega, 10 to the 6th.